And then we can welcome the second presenter, Ruijie Meng from NUS, to teach a little bit about how LLM, large language models, can be combined with fuzzing. So go ahead.
Okay, thanks for our session chair's introduction, and also welcome to everyone. I'm Ruijie Meng, currently a PhD student from National University of Singapore. My discussed topic today is large language model guided protocol fuzzing. This is a joint work with Martin, Marcel, and Abik. For the network protocols, I guess most of people are very familiar with that because some network protocols such as SSH and TLS may be widely used in our daily life. Actually, this is also why testing network protocols is very important because even a simple arbitrary code execution vulnerability may make many users suffer from remote attacks. But unfortunately, testing network protocols is a little difficult. This is because the network protocols are often implemented and stayed for reactive systems. So in such systems, if the bugs only happens in a specific state, but reaching this state, and we need to send the right messages in the right order. So we can see an example for the RTSP protocol. So this is the state machine for the RTSP protocol. So if one bug happens in the play state, and we need to first send the right message orders, and for example, we first send the setup message, and then play message to make the servers to reach the play state. And then we have the chance to expose this bug. And besides, each message also follow a specific structure. And for example, this is the message structure for the play message. So if the message structure is broke, and the message is also will become invalid, so it's also not able to introduce the state transitions in the systems. So you can imagine for testing tools, even for automatic testing tools, if they don't have the knowledge about the state machine information and the message structure information, it's actually very hard to generate the right messages in the right order. And unfortunately, the state machine information and the message structure information are often documented in the RFC documents. And they are often written in natural language. It's not a very strict specification. So for the automatic testing tools, it's actually hard to understand the state machine information and the message information directly. So in the fuzzing domain, there basically have two types of protocol fuzzing, and one is generator-based fuzzing. So in the generator-based fuzzing, it requires users to extract the state machine information and the message structure information from the offset documents, and then manually write a generator to generate the message sequence from scratch. But obviously, this approach will interest much manual effort. Actually, we have such experience try to extract the state machine information and the message structure information to construct the ground truth in our case study. So we spent several hours reading one document, and the whole process is very tedious. And after that, we are still not sure whether we construct a correct model, and we are also still not sure we are miss some information in the offset documents. We are still not sure whether we introduce the errors in the message structures. So you can see it's very hard to depend on the manual effort to construct the correct state machine information and the correct message structure information. So the mutation-based fuzzing tries to reduce the manual effort. And so it's also more widely used in practice. So in the mutation-based fuzzing, it uses some pre-recalled message sequence and the initial sets. So during the mutations, it will slightly mutate the messages and also message orders and try to explore larger and larger state space. So The mutation-based message fuzzing is obviously reduced the manual effort, but it still faces several challenges. And the first challenge is fuzzing the effectiveness is highly limited by the initial sets. So it's obvious to see that they use some initial test case as the mutation beginning. But the initial sets is actually very hard to cover the great diversity of the protocol state and the message structures. And so, for example, in the RTSP protocol, we still use this example. And so in a very widely used profile bench benchmark and the profile bench, its initial sets is only contain 4 types of client request. So actually, in the ground truth, there are 10 types. So you can imagine with the missing 6 type of client request, there will have a very large portion remains unexplored. This is the first challenge. And the second challenge is the fuzzers has no idea about message structures. So during its mutation, it's just random and some bytes, remove some bytes, or replace some bytes. So in this way, it's very easy to break the message structures and make messages become invalid. So you know the invalid messages is not able to be accepted by the servers and introduce the state transitions in the systems. It's also not help to explore different program behaviors. This is the second challenge. And the third challenge is the fuzzers also has no idea about the state space. So it's not because it doesn't have the knowledge about the state machine. So during the mutations, it's just random. So it's not able to infer the state space. So during the mutations and during the state selection, it's also not able to direct the fuzzings to explore deeper state space. And facing this challenge, and we try to, in this work, we try to use large language model to resolve these challenges in the protocol fuzzing. But why is large language model? This is because large language model, the capabilities have many implications for the protocol fuzzing. For example, network protocols are implemented based on the RFC documents. And the message structure information and the state machine information are also documented here. And so you know, large language model is pre-trained on billions of the text documents. And so they also have a very strong text generation, text understanding capabilities. So we assume large language model should also able to understand the RFC documents, and they should have such knowledge about the state machine and the message structures. And the second reason is the messages between servers and clients are often transferred in the text format. So you know the large language model have strong text generation capabilities, and for example, based on the specifications, and they can generate the code. So we think maybe based on the RFC documents, they can also generate the messages as well. The last reason is, you know, the fuzzing is often highly automatic and easy to use. So while we're using large language models, and we just need to provide some prompt, and then we could get the expected response. So we think even if we integrate large language model into the fuzzing, and we ask large language model could chant with the fuzzing, fuzzing can chant with large language model, and we still could keep the features of the good usabilities for the fuzzing. So, but this is just kind of our intuitions, and we are still not sure, and whether large language model really have such capabilities to resolve the challenges. So here we conduct a case study, and we studied the RTSP protocol in the lib5 implementations, and to check whether large language model have the capabilities to help us enrich the seed crops. And we ask large language model to generate 10 messages for each message type. So we finally get 100 messages, And in the generated messages, about 80% of the messages are correct, and which can be accepted by the servers and induce the state transitions in the servers. And to send the second challenge, and we want to see whether the large language model have the knowledge about the message structures. And we sampled the 50 answers from the LLM. And so in the answer side, and we are very surprised to see they cover all the message structures, and for each message type, and the message structures is almost exactly the same with the ground truth. And to see whether the large language model has the knowledge about the state machine, and so we try to give some message prefix and to make the servers to reach each state in the state machine, and then we ask the LM to infer what's the current state, and then ask it to generate the next messages that can potentially introduce the state transitions, and and then could potentially get the fuzzers to explore deeper state space. So we are happy to see that in the generated messages, about 70% to 90% of the messages can induce the state transitions to different states. And besides, this state transitions is also cover all the transitions for individual states. So these results are quite promising, and is also motivated by these results. And we proposed a large language model guided protocol fuzzing. And this is the overall algorithm. And the grid paths and the grid components as paths, and we try to enhance the existing mutation-based fuzzing. So the input is very simple. It's still the program and the test, and the corresponding network protocol, the name, and also some initial test case. And we hope to find some crashing seeds as our output. So before the fuzzing loop, the fuzzers first chant with the LM to ask the message structures, and based on the corresponding network protocol name. And after that, we also, based on some initial test case, the fuzzers chant with the LM to generate the missing types of the client request and try to enrich the initial test case. And after this, and this is actually try to address the first challenges. And after that, we enter into the fuzzing loop. And we first select the state that we want to exercise, and then select the corresponding state, and then we fuzz it. But this fuzz is not randomly to generate some, or remove or replace some bytes at this time. And we used grammar-guided mutation. And so in this way, we could keep the message structures is still valid, and we just mutate other parts. So after the messages is mutated, and we send the message sequence to the servers to see whether it can crash the servers. And if so, we save it and for debugging to see whether it's a real bug. And otherwise, we also see whether it can cover whether the servers can cover the new states or new code. And if so, we think the mutation is still interesting, and we save it for the further examination. And then after that, we enter into another fuzzing loop. But this is the state for relative systems, and without the state guidance, and it's very hard to explore deep state space. So it's very easily enter into the coverage plateau. So at this time, and we also monitor whether the fuzzers enter the coverage plateau, and if so, the fuzzers will chant with the LM based on the current communication histories between servers and clients, and then to ask it to generate the next messages that can potentially induce the state transitions and try to break the coverage plateau. This is the overall algorithm. And we implemented this algorithm as a protocol. and a prototype and called chant AFL. So in the evaluation, we try to see whether it can cover more states and whether it can cover more code and whether it's able to find new bugs in the well-tested subjects. So we select 6 subjects from the Profuzz bench. Profuzz bench is the widely used benchmark data set. And we compared our 2 chant AFL with the AFL-Night and NSFAS. And the 2 and the data set are publicly available here. So the artifact is also evaluated as available, functional, and reproduced. So in the aspect of the state coverage, and we are happy to see that chant AFL can achieve the same state transition numbers about 48 times faster than AFL-Night. And compared with ASFAS, chant AFL also can achieve the same state transition numbers about 15 times faster. And in the state coverage, and the chant AFL achieves almost 30% more states than AFL-Night and ASFAS. So in the aspect of the code coverage, and compared with AFL-Night, it achieved the same branch numbers about 6 times faster. And compared with ASFAS, it achieved the same numbers about 10 times faster. And besides, we also found 9 new bugs in the well-tested subjects. And so we also received 2 CVE IDs, and one severity level is critical, and another severity level is high. So we also try to use AFL-Night and ASFAS, our comparison tools, to compare it. And so in this bug data set, they can only find 3 or 4 bugs in this data set. So besides, they are also not able to find any else new bugs. OK, here is a short summary. So in this work, we proposed a large language model guided protocol fuzzing to resolve the challenges in the protocol, in the fuzzing protocols. So actually, these challenges is also very obvious, and many existing works try to address them. And for example, some existing work used reverse engineering or tender trunking to infer the message structures. And there are also some works try to infer the states. They use the response code or enum variables to represent the code and to represent the states, and then to derive the fuzzings to explore deep state space. So here we proposed a different approach to address these challenges. And actually, after our tool is released, and we get many feedback from the industry, and we are very happy to see that the developers integrate it into their workflow. And they think the tool is very effective, and the tool is also has good usability, and it's very easy to use to test their programs. OK, here is the end of my talk today. I'm ready for questions and also comments. Thank you.
So, any questions? Feel free.
A really nice talk. My question is, which large language model do you use?
It's the ChatGPT model.
Okay.
Yeah.
My second question is, in fuzzing, the throughput is crucial for fuzzing works, but communicating with ChatGPT is time-consuming. So what about the overhead with large language model introduced?
Yeah, this is a good question. This is also the issues that we faced in the evaluation and the implementation. And this is also why we try to address this issue is we are not sure how much overhead it will introduce, but it will introduce a lot of overhead. So we try to address this issue is we reduce the time to chant with large language model, but at the same time, we need to still ensure it's effective. So what we do is, before the fuzzing loop, and we will try to get the whole message structures and try to enrich the initial seeds. And so during the mutations, we don't need to chant with large language model again to get the message structures. So we just get the message structures once, and then we could use it for the whole fuzzing loop. So in the fuzzing loop, the only chance with large language model is if the fuzzers enter the coverage plateau, and this time, and we ask it to generate the potential messages to induce the seed transitions. And besides this, there is no other communications with the large language model. So in this way, we can reduce the overhead introduced by the chanting with the large language model.
Okay, that's good. Thank you.
Thank you.
Thank you very much. It's a really great talk. I just have a question about the input of the RFC documents. If I understand it correctly, your algorithm takes RFC documents as the input, and as you mentioned, the RFC documents are tedious, and so I would say the length and the information is so much. So did you, during your algorithm process, did you encounter any issues related to the ChatGPT or LLM input limitations? So just as I understand, you input the whole RFC documents to the LM, or just the part of or the section of that.
This is not true, and because we use the ChatGPT model, and the RFC documents are publicly available online. So actually the ChatGPT model is already have such knowledge about the RFC documents. So the RFC documents is actually not our input. Our input is just the protocol name, such as RTSP protocol, and then generate the message structures and like this.
Okay, thank you. So you mean that you just assume that the ChatGPT has already equipped the knowledge about the RFC?
Yeah,
okay.
That's true.
Thank you very much.
Yeah.
So let's send the speaker again.